Good morning, mathematicians. Welcome to another office hour. Hopefully, you're all having a fantastic weekend filled with proofs and
Good morning, mathematicians.
theorems and lemmas and textbooks. Always got to give my own videos a like. I'm sure YouTube doesn't count it. I'm sure it's like, yeah, I know that you're liking your own video. Whoa, Edit Smith, you're on the ball today, in before anyone else. Okay, what am I gonna yap about today? Until viewer questions start pouring in. Well, I've got some Reddit tabs open like usual, and and silly nonsense in my brain I could yap about. But let's see. There's some good questions here. What might have led to the concept of vector bundles? I have no idea. Well, I don't know what actually happened, but I think it's tangent spaces. I think that's just pretty much it. And then it was like, oh, well, if I can have one collection of vector spaces parameterized by points in my manifold, why can't I have others? Yeah, go ahead. Ask away. Ask all your questions. I'll also just quickly yap about what course changed your mathematical life. So I don't know if this is the one that said made me realize I wanted to pursue math. I think I maybe wanted that ahead of time. I do remember my very excellent it was like Calc 2 prof speaking very excitedly. We were doing like series and talking about infinite series, and I just remember like being like, I want to be like that. Like, I want to do that. Like, I want to talk excitedly about math in front of a room of people. But I think I already I already knew at that point, certainly, that I was interested in mathematics. But then the one course that really stands out to me is my Analysis 1 course. I think that's a course that made me a mathematician. I was still a big slacker before then. Even though I loved math, I hated doing homework. And so I got bad grades on a lot of courses, even though I could have had like A+. I just didn't put in the effort. And then that was the first course I had to put in effort just to keep up and follow what was going on. And that kind of like lit a fire in me. And I finally, for the first time ever, appreciated the joys of hard work. Was my master's thesis related to what I'm doing now? Was it about local Langlands or totally different? I mean, it wasn't totally different, but it also wasn't local Langlands. So, let's bring it up. So, yeah, the point of it, I mean, a lot of it was just some like Lie theory and differential geometry, really. But let's see, here's the introduction. Okay, so I say some stuff in the introduction, and, well, I don't understand everything I'm talking about in the introduction, to be honest. Well, in the abstract, I do. But I've never fully learned Shimura varieties properly. And secretly what I'm working with here is Shimura varieties. So, yeah, the point is, I mean, this is related to Langlands. It's something to do with there's something called the Weil representation. And that actually exists in local Langlands, in real Langlands, and all of these things. It's a way to build certain like irreducible representations. Okay, and I was studying the Weil representation for this group, the unitary group UPQ, and and so we can see here. So right in this line here. Well, the first line of the paper actually says a lot. So a special cycle of a certain Shimura variety. So whatever the Shimura variety is, a special cycle is like some special subvariety of it. And so, okay, the local Archimedean height. So this is all in Archimedean world, and I work in like p-adic land now, except for all the algebraic geometry I do. But yeah, so the height, it's some piece of data attached to a special cycle in terms of a Fourier coefficient of a special derivative of an Eisenstein series. Okay, so Eisenstein series, that's like very Langlands-esque, although these are different than the ordinary Eisenstein series. They're souped up. Yeah. And then it goes on to connect so it's building on previous work of my master's supervisor and collaborator that does some stuff about Chern-Weil theory, so some differential geometry, and somehow you connect the Weil representation, so this like Langlands type representation theory for some real Lie group, and you connect it to differential geometry. So, I mean, in a certain sense, it's very similar. It's very related. In another sense, it's very, very different. Because this was, in the back of what was going on, this was to have applications to the real theory, to representations of real groups. But I guess in both cases I ended up doing, here I ended up doing a bunch of like differential geometry for the project, which isn't so different than what I'm doing now. I mean, maybe it's more algebraic geometry, but there's like a mix of both things in there. So, yeah. 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 So, hopefully that answers your question. Also, we have a post here. How much do you read as a researcher? I'm a grad student in the process of writing my first paper. I've been reading a lot less mathematics. Oh, interesting. Most of my reading nowadays is little snippets from various papers that are relevant to my problem, along with other things that I read to present in seminars that I do with other students, which are fairly irrelevant to my research. I feel like this is okay, as I should use grad school to widen my knowledge as much as I can. True. I mean, I don't know. I'm always torn by this. I'm like, but if I was just more focused and narrow-minded, maybe I would have way more papers by now, because I would have just worked harder at these singular things. But then, grad student life, even though it's a lot of work and you have a lot to do, it's probably the last time you'll ever be truly free for the rest of your life. And so, I guess it just becomes harder to find time to do stuff. It's easier to make time to learn these extra things while you're in grad school. So I don't know. I want to agree with this, but I'm also biased because I'm naturally someone that just gets distracted by shiny, interesting things. So am I just justifying the way that I already am and saying, oh yeah, that's the good way. That's the way you want to be. I don't know. Is it normal to not read as much as a researcher? Do you ever find yourself dedicating time to just reading papers all the way through? Absolutely not. Well, I mean, okay. I'm basically in this person's shoes, so I shouldn't be considered as a authority on the best way to spend your time to produce papers, but I absolutely, I think I've talked about before, like I do not understand all the proofs of all the papers I've read, like like if I like, okay, all of these I'm not saying that I used for sure every one of these papers in this folder right here, but like I downloaded all of these for a reason. You know what I mean? Whether I like there was something I needed to read in there or understand. A lot of these ultimately I did cite at some point or something. And then okay, those are just the folders in the loose files. I also have some stuff that's like categorized by different topics. So it's there's a lot of stuff, and there's no way in hell I understood every proof in every paper. Absolutely not. I mean, I barely understand any of them. Like, so one fundamental thing at the beginning of my research was it periodic representations of periodic. I was hoping it would just come up if I searched it here. No. Here's what I need to search. Induce 2. That will come up. Yeah, so one of the earlier papers I read relevant to my research is this paper by Zelevinsky on multi-segments for GLN, and like, I don't think I think to this day I don't understand like most of the proofs. I just took it as like a black box. I just said, okay, this is the, the stuff here is like the representation theory for GLN. I just accepted like, okay, the supracuspidal representations are these mysterious things. We're going to take those as a black box, and we're going to build all of our other representations out of these supracuspidal representations. And then I read the paper enough to get how things worked. I mean, I guess it's not like I ignored all of the proofs. Like, in order to see how the pieces move, you look inside the proofs and stuff. But I mean, this is maybe I should go back and understand these things, but because this is such a foundational and important paper. But I don't know. There's only so many hours in the day, right? And it's like, especially in something like Langlands, it's like if you spent all your time trying to have all the background you're supposed to have before starting research, then suddenly you'll be like 60 years old and you'll have not published anything, but you'll know all the background of Langlands. So I don't know. Maybe it'd be nice if I was just I should have been a finance bro early. I could have retired by now, and then I could have just spent the rest of my life learning all the background of Langlands. That'd have been nice. But this is pretty good too. Read everything, non-fiction, of course. Well, why not fiction as well? Fiction's good. I mean, definitely I don't read as much fiction as I used to. Like when I was a teenager, early 20s, I was quite a voracious reader. Like I devoured a lot of books. And now, I almost feel like guilty. Well, it's not just guilt, but it's also desire to like, I want to learn more math and understand more math. So I only read at night now. Sometimes I'll read a bit before I go to bed. But actually the book I'm partway through is, I haven't touched it for a couple weeks now. Yeah, normally it's part of my bedtime routine, but Reading Langlands is fiction. Okay, true. True. All math is fiction, actually. All math is a useful fiction. So, absolutely true. I guess I read a ton of fiction. I still read a ton of fiction. Some things never change, I guess. Oh, speaking of stacks, I do have this stacks document open here. I haven't seriously started reading it, but ever since I mentioned, I was like, oh, maybe I should do a stack stream. I started taking a look at it. Would be good to understand. Do I get to go to a lot of conferences, and how much of an expert in a subject would you say one has to be for it to make sense to go to a conference? I would say you can be 0% an expert to go to a conference. Yeah, just go. Just go. It makes tons of sense. Go to a ton of conferences. I'll bring up a list of all the conferences I've been to in a moment. But let me talk about one particular conference I went to when I was in undergrad. So it was the WAGS, Western Algebraic Geometry Symposium. And I was ill-equipped to attend this conference. I understood basically nothing in like most of the talks. I knew some very, very basic ideas of algebraic geometry, but otherwise I was unprepared. But it was still, I don't know, I think an enriching experience. And I think at least then, WAGS, like, they paid for my flight. So I just needed accommodation, and I used couchsurfing.com to just, stay with some random person. Because there's a great, if you travel a lot, that's a great online community that allows you to travel for cheap. And you get to meet interesting people in random parts of the world. And so at the very least, if you go to a conference and you don't understand anything, well, you get to spend some time in another city and see the world. So I got to see San Francisco for the second time. Actually, I'd been when I was younger, but I got to see San Francisco, and that was awesome. But then also, so there was something, I guess, a failing on my part, but so I remember, we went out for drinks one night, a bunch of us at the conference, and I was talking to some people from Colorado. There was like a number of people from the math department there, and they were just so stoked on the fact that I was there. They had no idea, like, whether I understood. Like, I guess they probably had some sense of what I might have understood or not. Because, I was asking people questions during drinks. I was, like, asking them to explain some, like, super basic things to me or whatever as the conversations, like, were happening mathematically. I would ask some questions. Yeah, sorry, I know it's Vistoli. And then whenever I downloaded this PDF like 100 years ago, I accidentally typed a Vitoli in there. Yeah, I guess I should change it, but yeah. Sorry to Vistoli for that, but anyways, so I was talking to these guys, and they were just so thrilled that I had the like gumption to go to this conference that I was like just so proactive about it. And they were like, hey, when it comes time for you to apply to masters, like, get in touch with us. And now here's where I made the mistake. I should have kept touch with them all along. I did get some of their emails, but, by the time I was ready to apply for my master's, I think like some people had already left or moved on, and some people had like forgotten about me. So what I should have done is just emailed them all immediately after and said, hey, just like making contact, blah, blah, blah. Maybe ask them some questions about like, oh, what do you think I should read or something, right? Just keeping that line of communication open. And then probably that would have been a really good in to go do algebraic geometry with those people at that university. I mean, things still worked out well enough for me, and I love where I am now. I certainly don't have any complaints, but that's just more opportunity, more chances, more options I might have had for grad school. So 100%, even if it's I just say go to conferences, go to all conferences, go to all summer schools you can possibly get your hands on, that you can afford, that you can like get funding for. Go to as many as many of these things as you can. And there's things at all different levels. Like there are some that are specifically designed for undergrads. There are ones like that are advanced. There's ones like the CTNT. It's like the Connecticut Number Theory School. So there's the actual conference, but then a week before there's like a school, like a little mini school for, I think, undergrads and grad students. So there's just so much out there. It's really nice to hear. Been looking at the types conference on type theory. I've been looking at type theory, but sadly it's not a big deal at the math department at Copenhagen. Yeah, so go. Just go. Make some connections. If it's something you're interested in, absolutely. How do I feel about hyperbolic geometry? I love hyperbolic geometry. Well, mind you, I don't know. I say that, but do I do a lot of hyperbolic geometry? Actually, let me tell you about some of my favorite hyperbolic geometry in a moment. But first, let me show you all the conferences that I've been to, because I've done a lot. I don't even know if probably all of them are on here, but so it's probably not common to put them all on your CV. But okay, so I've given a couple of invited talks at CMS on the topic of my thesis. We also, a bunch of us at the University of Calgary, organized a graduate mathematics student conference for grad students in Alberta, but we also I think every year we've done it, there's been people from like neighboring provinces or the northern states have come up as well, just as it's like, oh, we applied for funding, we had some, we just send out the applications, and hey, if we had enough funding to help support other grad students from nearby coming on, then we did. But yeah, so here's look at this list going all the way back to so here's the 2018 Western Algebraic Geometry Symposium. That was the one that was the one I was talking about. But before that, I did a discrete math workshop went to a discrete math conference. So the 2017 and 2018 Western Summer Schools in Algebra, that's actually where I met the person who put in a good word for me with my current supervisor. So Calgary wasn't even actually on the map for me. I hadn't looked at it yet. I had already applied a bunch of places, and I was talking to a friend I had met there. Me and her had kept in touch over the years, and she was like, "Oh, I think you would really get along with this guy. He's one of my profs. I'll put you two in touch." She put in a good word for me, and now here I am. So, okay, there's two examples of reasons you should just go to random stuff. I mean, this one was more targeted at undergrad specifically, but yeah. So I've gone to all of this crazy. I've gone to all this stuff, right? Arithmetic topology, mirror symmetry, and I don't do anything. I don't remember most things about the mirror symmetry thing, but again, it was a chance to go. I think that one too. My flight was paid for, so I got to go fly to some other city and meet a bunch of people and study math together with them. And actually, a lot of people at this one. I sort of reconnected with people from the Western Summer School in Algebra. So, yeah. And speaking of proof assistance, I've also gone to a conference or to a summer school on homotopy type theory, as well as a conference on formalizing cohomology theories. So yeah, I mean, in my opinion, that's one of the best parts about being like an academic is like people just give you money to go somewhere and learn math. Like, okay. I guess I need to add in here the one I just went to in Maryland. So I went to go see Maryland. I got to see like the U.S. Capitol and go hang out and learn about math there. So I don't know. Just do it. Okay, well, here's one thing I love about hyperbolic geometry. I love triangular tilings. Can't spell. Refuse to learn now. I love triangular tilings. In particular, one of my favorite ones, let's see if they have it here, is Klein's chordate curve. Klein chordate curve. Yeah, so here's John Baez's. So here's like a compactified version of Klein's chordate curve. But also, yeah, so here's another way to build it is you take heptagonal tiling, and you can only take like a regular heptagonal tiling if you do it in hyperbolic space. And then what you can do is there's sort of a natural way to like curl it up so that you get these you get this shape that's like rotating here. So it's really I think it's cool for a lot of reasons. Reason number one is it's connected. It has connections to the Fano plane. So I don't know. Where's a picture of the Fano plane here? Yeah, the Fano plane, which I actually have. I don't know if you can see tattooed on my ankle here. It's the smallest finite projective plane. Oh, Smicky Dibbly. Looks like candy. Yeah. I mean, that's also why the main reason I'm in mathematics is because I'm trying to understand enough math so that I could eat Klein's chordate curve. I don't just mean print out a model of it and eat it. I mean like eat the the concept of Klein's chordate curve. Haven't managed it yet. So yeah, why else am I obsessed with this? Actually, Smicky Dibbly knows about my borderline numerology obsession with this thing. The other thing too is that you can think of it as kind of a higher genus Platonic solid. So like here we have, so here like you attempt to tile something by, yes, they definitely would make sick album covers. I agree. But yeah, so if you attempt to tile something by triangles, you get a tetrahedron. You take its like dual, it's just itself. You try and tile something by squares, you end up getting the cube, and then its dual is the octahedron. And then you try and tile something by pentagons, and its dual is the icosahedron. And so that is all of the Platonic solids. But then you could go and ask, well, what happens if I try and tile something by hexagons? And then, well, that sort of you have to now do it on this infinite sheet. You can't curl it up on a sphere. But again, since it has this periodic nature, you can cut it off and then curl it up into a torus. And so a torus tiled by either the certain kinds of triangles or hexagons can actually be thought of as like a genus 1 Riemann surface. Then you go up to heptagons, you get Klein's chordate curve. That can be thought of as like a genus 3, as a genus 3. Oh, sorry, did I say Riemann surface? I mean, Yeah, of course a torus is a Riemann surface, but I meant a genus 1 Platonic solid. This you can think of as a genus 3 Platonic solid, and so on and so forth. But actually, part of my obsession is, so I think I talked about this I have an old video called Why I Love 168. And I talk about a bunch of the things I'm about to say here, but I'm obsessed with this problem in graph theory called the Moore graphs. And I mentioned on this in my office hours the other week as well. So you're looking for a graph that is k regular with k squared plus 1 vertices. I'll just let you Google these terms later. So girth 5 and diameter 2. And it turns out the only possibilities are the only possible values of k are 2, 3, 7, and 57. K equals 2 is the 5 cycle. K equals 3 is the Peterson graph. And both of these are the unique graph for k equal 2 and 3 up to isomorphism. And then k equals 7 is the so-called Hoffman-Singleton graph, also unique up to isomorphism. And it turns out that one of the ways that you can construct the Hoffman-Singleton graph is out of using a bunch of Fano planes. So that's one way that you can construct the. So that's part of my obsession with Fano planes, which are now the copies of the Fano plane. This construction's in Godsill and Royal, but then the open question is about 57. Yes. Okay. Yeah. Yeah. So. I don't want to believe it's a coincidence. But check this out. So the number of 5 cycles in the Peterson graph is 57. Also, if you look at the Hoffman-Singleton graph, you can ask, so you see how the way that we draw the Peterson graph, like we're just sort of forced to draw it with lines crossing. This is just true. You can prove that no matter how you draw the Peterson graph, some of those lines will cross. But then you can ask, okay, what if I drew it on other surfaces? Like how many times do I have to puncture a surface in order to draw it? So you can actually draw the Peterson graph without crossing if you do it on a Mobius strip or if you do it on a torus. So the genus of this we would say is 1. Well, because the Mobius strip is non-orientable, and that's the smallest non-orientable surface we can draw it on. It's got 1 hole in it. It has non-orientable genus 1. So the Hoffman-Singleton graph has non-orientable genus 57. I mean, maybe it's just a coincidence, right? But I feel like, come on, if this last graph exists, there should be some reason, there should be some relation between them that this is that's controlling all of it. The Fano plane also gives multiplication table of the octonions. Yes, absolutely, yes. It's another reason why I love the Fano plane, because it's connected to the octonions. And then the octonions, in turn, actually, so the octonions are closely related to the E8 lattice. And there's something I don't quite understand. Oh, yes. Okay. So tastes like moonshine to me. Yeah. Yeah, this graph with 3,250 vertices, it's too difficult to brute force. I once tried playing around with an algorithm that I thought would construct it, and I did. The algorithm I came up with, it does construct a connected subgraph of it, And you're just using basic properties of the graph to force like vertices and edges between them. But I think it only had like 5% of the edges before the algorithm like can't go any further. So yeah, I mean, it's hard to search. And that algorithm ran for a day. And that was sort of constructively trying to force some substructure of the graph. And this algorithm ran for a day and produced like maybe 5% of the edges. Yeah. So, so the octonions are connected to the E8 lattice, and you can basically build also the Leech lattice by gluing together 3 copies of the E8 lattice in a certain way. And guess what? You can find a copy of the Hoffman-Singleton graph sitting in the Leech lattice. So I believe John Conway, actually, here's a funny story about him. Apparently, allegedly, one day he just decided he was going to find some of the missing finite simple groups. And then that was on like Friday. And then by like Saturday night, he found them. He found like 3 of them. And I believe those were the ones that he found within the Leech lattice. He basically he constructed them as groups acting on certain points of the Leech lattice. One of these is, I think, the Higman-Sims group, which contains the automorphism group of the Hoffman-Singleton graph as index 2. Yeah, graphs are so beautiful sometimes. 100% agree. Yeah, I mean, this is big. This does have big Moonshine vibes for me. I mean, this is why. Okay, I mean, I don't spend all my time doing the. You know, my ranting here is basically numerology, right? So it's not founded on strong mathematics, and I spend most of my time, doing real, actual things that other people care about. But I can't help but dream. Let me go back to my site here. I've got some of my favorite quotes. Yeah, we can count the number of 5 cycles. It's actually very easy. It's right at the top. In the broad daylight, in the broad light of day, mathematicians check their equations and the proofs, leaving no stone unturned in their search for rigor. Actually, I've read some pretty non-rigorous papers by experts, but I digress. But at night, under the full moon, they dream. They float among the stars and wonder at the miracle of the heavens. They are inspired. Without dreams, there is no art, no mathematics, no life. So, yeah, I hang on to this quote by the famous Sir Michael Atiyah, that, you know, one day maybe my insane dreams about there's something here like the missing Moore graph, you know. I feel like maybe it's got to do something with the Leech or maybe a larger lattice yet built out of it. But that's my hope. That's my dream, right? There's some circle of ideas here, right? Octonions are related to the Fano plane. The Fano plane constructs the Hoffman-Singleton lattice, but the octonions also give you the E8 lattice. 3 copies of that give you the Leech, and then the Leech gives you back the Hoffman-Singleton graph. Also, there's some relation, I don't know what it is, but there's some relation between the Peterson graph and the E8 lattice that I don't totally understand. It's in Godsill and Royal. This is something I really want to understand better one day. Nice quote by Baez. Yeah, Baez. I've never known. The comment was meant to be encouraging. Yeah. Moonshine did work out after all. Yeah, but yeah. So that's what I hold on to. I'm like, yeah. If this guy noticed that like n+1 equals n+1 could turn into something, then why can't my insane dreams, which have borne no fruit in the last 10 years, not lead to something? Actually, that's not true. I was talking about how I think I have an idea for a paper in graph theory. It's now not related to the Moore graph problem, but actually just solved something. I think maybe I could have a publication in graph theory from an idea I got that was born out of my original searching. My original searching there. But yeah, so there's something. Where is it? I think it's in the section on Laplacians. Laplacian matrix. Root systems, yeah, line graphs and eigenvalues, root systems. So there's some connection here. I haven't fully understood what's going on in chapter 12 here, but there's some connection between like root systems and certain kinds of graphs, and like figuring out like I think you can determine if a graph is a line graph or not if something about its Laplacian matrix is maybe connected to like the Cartan matrix of the root system or something. And so it's through there that somehow the Peterson graph has something to do with the E8 root system. So maybe if I better understand that, I'll understand all the secrets to the universe here. And then also, this is more so to bring things back to Klein's quartic curve. There's something about so if we take so I think one of the ways to construct Klein's quartic curve is you take the modular curve. I think we read it like this, like x7 mod gamma or x7 right, x7 is like, it's like the upper half plane modulo the group gamma 7. And this gives us some example of a modular curve, and you can get a whole bunch of, what is it, the Hurwitz groups. Let's bring that up. Hurwitz groups. Wouldn't it be great if one day I had like such a famous math podcast that I had my own Jamie, like on Joe Rogan? I could be like, Jamie, bring up the Hurwitz groups. Yeah, bring up that paper. Actually, I love doing it myself. Yeah, okay, so we've got the Hurwitz groups, right? So to obtain an example of the Hurwitz group, well, the 237 triangle group, yeah, so I mean, we're just getting the Klein's quartic curve again. But then there's some theorem that says somehow we get the Hurwitz groups all of like some sort of quotient of this one. What is it? No, this isn't the right. I don't think I haven't looked at this in years, so I don't remember where the thing is that I'm looking for. But there's some sort of relationship here with the Klein quartic curve particularly, and you take like further quotients of that to get the other yeah, I don't remember, but there's some connection here that I don't remember about the other. You can get some of the other finite simple groups in relation to Klein's quartic curve. It's gonna bug me now. Like, what if I just look up like finite simple group Klein quartic? What does AI think? Yeah, it's just gonna tell me that PSL27 is simple, but that's not what I'm looking for. Yeah, what is it? It's some of the sporadic groups. Yeah, maybe if I put in sporadic group. Yeah, I'll have to go digging again. Yeah, I think definitely. Yeah, maybe there's something on the, because I think this was one of them. The Matthew groups. Is it pronounced Matthew? I have no idea, because it's spelt weird. So I assume that I'm mispronouncing it. There's something here. Okay, Fano subplanes. Yeah. Yeah, there's something going on here with this one. Anyways, yeah, that's a circle of ideas I'm absolutely obsessed with. I don't even remember the question that got this started. Oh, the question that got this started was how I feel about Matthew, Muth, I don't know. I don't know. I'll have to ask. I guess I can just ask Google. There's like, yeah, what a great world we live in now, where Google will just tell you how to pronounce things. Anywho, yeah. So that's how I feel about hyperbolic geometry. I'm obsessed with Klein's chordate curve. It's such an amazing thing. And okay, this isn't. One of the Mutheu. Jealous of anyone whose name has math in it. Yeah. Well, that's why my Discord handle is I took Kristaps and I replaced the I with a 1. So now it's got math in it. But it's not as literal as Mutheu. Not as literal as Mutheu. I'm just gonna name my children after theorems, I think. Yeah. And then that'll be really confusing if my children who are already named after famous theorems go on to prove famous theorems of their own. But whatever, life's meant to be confusing. Muth as in muteu. I'm slowly getting there. The question was, how do you develop a good feel for... I can't even read. How do you develop a feel for hyperbolic geometry? Oh my god, I can't even read. I just ended up going on this rant. I don't know. I don't know if you're still... I don't know if you're still in chat, but let me... I have mathematically inclined birthday, but don't want to share identifying information with random people on the internet. That was probably a good idea. I probably shared too much information with you seeing all of this on my screen. I've probably given away way too much. But yeah, there's 2 Borels. I didn't know there was 2 Cartans. That's good to know. That's good to be aware of. I did know there was 2 Borels. Did not know there was 2 Cartans. There's also 2 Gabbers, right? And there's proofs out there by Gabber, or husband and wife, I believe. That's the dream, isn't it? Husband and wife dream team proving famous theorems. That's the dream. Inclined birthday. Where was I? Oh yeah, how to get a feel for hyperbolic geometry. Well, one thing I would do is, so there's a book, actually, so generally speaking, I don't love this book. It's the book that the University of Manitoba used for, yes, there's also 2 major Conways, John B. Conway and John H. Conway. But there's a book, Deepak, I'm not totally sure I understand what you've written there with your fractions. But there's a book, Mathematics in Art. I'm sure you can learn this other places, but it's the book that at least they used to use for this course. Does it say? It was like the math course that we made art students take at the University of Manitoba. Yeah, this is the one. Math and Art: An Introduction to Visual Mathematics. And honestly, I think it was. I thought it was really hard, to be honest. I thought it was a really hard course for art students. I'm like, I don't know, like maybe it was a little much. But what was really cool is that's actually, we don't teach ruler and compass constructions anymore in school, and that's where I learned about ruler and compass constructions, and that's actually why, I have a 4-part series on the geometric impossibility theorems. A little 4-part video, and I actually show you like how to do ruler and compass constructions there, which I learned from that book. And in particular, they tell you in that book how to wow, it's so awesome that OneNote just does that now. It's amazing. I love it. I mean, actually nothing happened. I'm just perfect at drawing circles. But they give you a way to construct the hyperbolic disk, and they actually tell you what the lines are, and the they tell you what the lines are, and they tell you how to actually do this with like a ruler and compass. So like they'll tell you how you can construct a line here, and this is like a straight line, a hyperbolic arc, and there's little problems about like, prove that if you have like 2 hyperbolic lines, like you can find another one that intersects one of them or something. So one way I would recommend to get an intuition for hyperbolic geometry is go look up this. Go look up ruler and compass constructions for hyperbolic geometry, and do some like basic problems and exercises on it. I think that'd be a great way to get some intuition for the what would be called the Poincare disk model. Yeah. Okay. So now I'm behind in chat. Guessing math birthdays. Yeah, I'm absolutely slow all of the time. So I don't know if this person is still in chat. But hopefully that gives you some idea of what to look up. Maybe I should make a video on this. I think I might have a digital copy of that book somewhere on my laptop from when I was TAing it. I could probably look up the notes and talk about ruler and compass. Can't even speak. The constructions, because I think that's a missed part, especially in like Galois theory class. We talk about the geometric impossibility theorems, but like it's just not the same. I feel like if you haven't like held the ruler and compass in your hand and like done the constructions yourself before, on the line of how many 5 cycles, on the line of, let me go back to that before. I know there's more questions in chat, but okay. Actually, do I want to count it? Okay, let me give you the answer. Here's homework, Chalex. Here's some homework for you. So I claim that in the Moore graph of degree k, or of degree k, I claim that there's this many 5 cycles. Times do I remember how many there are? I think it's k times k minus 1 over 2. Yeah, there's this many 5 cycles. So that's everyone's homework. Is to do some basic combinatorics and convince yourself that's true. Here's another thing that I think is very interesting. I haven't been able to prove, but I don't think it's a coincidence. So for example, let's take the Peterson graph, and we can by cutting some edges, we can partition the Peterson graph into a collection of disjoint 5 cycles, such that each vertex is in one 5 cycle. So I just snip the connecting edges here so that each 5 cycle is in one, each vertex is in exactly one 5 cycle, and none of the 5 cycles share a vertex. So for any of these graphs, right, you're just taking the number of vertices and dividing it by 5, right? So that's this term here. What's very interesting to me is that this term appears to be the number of ways that you can partition the Moore graph of degree k into that many cycles. I don't have a proof for this in general. I mean, it's just obviously true for the 5 cycle. I counted it by hand for the Peterson graph, and I also found some slides which I was able to figure out that it's true from some slides on a talk about the Hoffman-Singleton graph. So I don't know that it would still hold for the missing Moore graph. In fact, I don't know if you can even partition it like that once. But there does seem to be a pattern here, so that makes me think that there should be some general theorem that one could prove. This is also, you can build an F2 vector space out of the not the cycles, it's called cycle space, but the circuits of your graph, the Eulerian subgraphs. And this is also the dimension of cycle space in each of these cases. And that I can prove. That's a very easy thing to prove. So like, I don't know. That's interesting to me. That's it feels like, I don't know, there should be something going on there. Anywho. Okay, what was the biggest roadblock in understanding category theory for myself, and what advice would you give to someone that is currently in a roadblock? Biggest roadblock. I don't I don't know if I personally feel like I hit a big roadblock. Not to say like, oh, I'm so smart, category theory is easy or something, but I don't know, like a roadblock. Like I know what it means. Like I know, like I've been stuck in my own research or something. But for category theory, I don't know. It's just like when I'm hungry to learn more, I learn more. So I'm not so sure with myself. I don't know if I can point to a particular roadblock. Maybe if there was something I didn't understand, I don't know. I just kept trying, or I stopped and read something else for a while. To be honest, I don't know. Well, I mean, okay, I've done some reading on infinity categories, and I find that very confusing. But even that, I mean, I don't know if I. So I'm not sure. I'm not sure. What advice I would give? I guess it depends on the nature of the roadblock, right? It depends on. Depends on a lot of things. But if you're just in a roadblock at learning category theory, then I mean, probably the number one thing to do is find other books on category theory. Like what is the main reference you're using, for example? Find other references. Consult those other references. Talk with people online, or rope a friend into learning category theory with you or something. Those are all good ways. So that's what I would say is maybe expand your search space. But it's harder to know without more information about like what your particular roadblock is, like what it is you're struggling with, or because with more precise information, maybe I can give you a better idea of what the way through is. If I have a 3-hole torus, the fundamental group is SU2. No. A torus, a 3-hole torus. It should be easy to compute the fundamental group, right? I mean, the fundamental group of a single hole torus is just Z cross Z, right? Why do I feel like it should be a free product, though? I know it's not, right? Because a torus is just S1 cross S1, and the fundamental group preserves products. So it is absolutely Z cross Z, right? Why am I feeling like it's some sort of free product? But then, no, I don't think the fundamental group will be, I don't think the fundamental group will be SU2. Gotta think back to my, I mean, the way to do this would be to, use the, what's his name? What's the theorem? Van Kampen theorem. Yeah, Van Kampen theorem. So, you got to take some open sets. So you take one open set, I guess, which is this torus, and you take the other open set, which is this torus, and then you got to compute the fundamental groups separately of each of those open sets. So we have like we basically have a Z from over here, a Z from over here. And then the thing in the middle, the intersection of those two, will be this little tube. So we have another Z here. And then Van Kampen should say that it's like some, it'll be like some sort of product like this of the oh sorry, no, these are both Z2s because it's the torus. Oh wait, but oh gosh, no. Now I'm confused because we have this opening here. Yeah, we gotta do more. We gotta do more work. But I think there's a very simple combinatorial, like I think there's a theorem that basically just says like pi1 of the torus with like h, like a torus with h holes is just, and then we can write something. Like I actually remember in my algebraic topology course, we even gave like a combinatorial classification where it's like, I think you take like the direct sum of an h-hold torus and like a h like Mobius things, and I think we gave some like combinatorial proof of what the fundamental group is, but I'm pretty sure it's not SU2 anyways. Sorry, lots of stuff happening in chat. Yeah. Had a class on that at a math camp in middle school, but used a half plane instead of the disk. Yeah, a half plane model is great too. I like the disk. Tom Leinster's notes on Galois theory, chapter 5.3, has some stuff on it. Has some stuff on. Is that the where you were stuck? Is in Leinster 5.3. Oh no, we're talking about Galois theory and SU2. Yeah. Homework. That's another thing. Well, you better do your combinatorics and graph theory homework from this stream. Leinster's book is very approachable. Yeah, if you can follow it, then anybody can. Yeah, I recommend Leinster 100%. But I don't know. Different people have different opinions, right? So maybe not everyone. Everyone just likes to learn from it in that way. Has the same learning style. I mentioned earlier that Peterson graph has 57 5 cycles. Correction, it just has 57 cycles in total. Ah, yes. Sorry. That's right. So that actually would contradict this formula I came up with. Not came up with, but formula that I wrote here. Yeah. So sorry. Yeah. Let me thank you for pointing that out. Yeah. The number of cycles period in the Peterson graph is 57. This is true. Whew. Z to the 6, do you think it is for Z to the 6? I mean, it could. Why? Yeah, I don't know if it's Z to the 6. Maybe that's homework for me to do, is remind myself. It's been a million years since my algebraic topology course. Where's my courses? Documents, courses. Where's algebraic topology? Algebraic topology. Notes? Maybe it's in my notes. It's definitely in my notes. Group theory. Where would it be in here? Look at these trash notes. I don't even have a. Oh, I do have a table of contents or clickable things. Okay, so that's fine. My notes weren't so bad. But let's see. Do I have the theorem here? Van Kampen. Lens spaces. I know that we. Maybe I should go to the course notes. This is the book we used. Same author from the math and art course. It's got to be in here somewhere. I'm pretty sure there's the classification of the stitching together tori. CW complexes. Yeah, maybe I'll have to do. Oh yeah, compact two manifolds classification 343. Hell yeah. Oh, where'd my chat go? You can just count the number of non-contractible closed loops. Can you, though? I mean, I don't know. Things get weird. There are 6 distinct loops. Yeah. Okay. I guess I believe you guys. But we're at the classification theorem anyways. Every compact connected two manifold is homeomorphic to a sphere, connected sum of finitely many tori, or connected sum of finitely many projective planes. Right. Yeah, and so I think after proving this, we give the classification of their fundamental groups. Yeah, I'm also not so sure either. Let me maybe tomorrow's stream I'll use Van Kampen to prove what the fundamental group is. Oh yeah, maybe this is the better way to draw the picture actually, to use the like standard construction. Is this here? Yeah, fundamental group of compact two manifolds. Spheres are simply connected. Start by identifying polygon. Okay, just tell me the statement. What is it? Here we go. So the connected sum of M tori, this is the fundamental group here in terms of generators and relations. Yeah, so is that really just going to be Z6? So we'll have A1, A2, A1, B1. So 3-hold torus. For a 3-hold torus, it should be, for a 3-hold torus, the fundamental group. I didn't draw a 3rd hold. No, 2-hold torus. We're doing 2-hold torus. How many hold torus are we doing? We're doing a 2-hold torus. So it should just be A1, B1, A2, B2, subject to the relation A1. What is the relation? Let's look again. Aha. A1, B1, A1 inverse, B1 inverse, times A2, B2, A2 inverse, B2 inverse equals 1? Ooh, that looks terrible. It's completely unreadable. Yeah. Now we need to figure out if that's isomorphic to z to the 6 or not. But the word problem for groups is undecidable. Surely it can't be that hard. Surely it can't be that hard. Yeah, I don't know. I'm going to have to think about this. But my coffee's done. And my proofs are waiting. God, this has been a long stream. I've been ranting about all sorts of stuff. There's going to be too much stuff for me to fit in the title. Oh well. That's it. It's time for me to prove some theorems. It's time for you to prove some theorems. Let's go get this bread.